Okay, so next what we looked at was we were looking at terminal velocity. We were looking at free fall. So when an object is in free fall, well, it's going to experience. If first of all, if there's no air resistance, it will experience one force, and that force is called weight. So by definition, weight is equal to it's the force that something feels due to gravity, specifically when it's close to the surface of a planet. But we can just forget about that last bit. It's the force, like an object is. If I drop this pen, it's going to feel it's the force that it feels to pull it towards the table is called the weight, and that weight is equal to, it can be calculated by the mass multiplied by the gravitational field strength. So what is gravitational field strength? It's how strong the gravitational field is. So gravitational field strength on Earth is 10. Well, actually, it's let's be a bit more precise. It's 9.81 newtons per kilogram. So every kilogram of matter will feel a force of 9.81 newtons. So the weight would be equal to whatever amount of kilograms multiplied by the strength of gravity. And if you think about it, we know that because of F equals ma, I can rearrange that to be A is equal to F over m. And if F in this case is the weight, which is mg, well, then we'd say mg over m. And now we end up, the m's cancel out. And so that means that the acceleration in free fall is the same as the gravitational field strength. So when we say that G is 9.81 newtons per kilogram, we could also say G is 9.81 meters per second squared. That's the unit of acceleration. So the acceleration at the very start of when something is falling will be equal to the gravitational field strength. But as soon as the very instant it starts moving, if it's moving through any sort of fluid, and when I say fluid, I mean a liquid or a gas, anything that can flow. So it's a liquid or a gas, not just a liquid like most people think. So for example, if it's moving through air, as soon as it starts moving, which is as soon as you let go, then it would experience a certain amount of air resistance or drag. And the drag is proportional to the speed it's moving. So the faster it moves, then the greater the drag. So if we looked at this over here, and we imagine a man falling, he's got his parachute ready, but he's not opened it yet. So at the very start, when he hasn't yet started moving, then the force is it's negative, because when we say a force is either negative or positive, it depends on what direction we consider to be. We decide what direction is positive. So in this case, they've said up is positive, but it's totally up to you. As long as you're consistent, it won't matter. It won't matter at all. So they've said up is positive, so therefore down will be negative. And so the acceleration is negative 9.8. I said 9.81, but yeah. And as soon as he starts moving, a drag force starts appearing. Now, the resultant force is still 582, or negative 582 if you like. So there's still acceleration, which means he's still going to speed up. But gradually this acceleration reduces to 0, and at that point, the forces cancel out. Now, when the forces cancel out, he's still moving, he's just not getting any faster, because acceleration is equal to F over m. That's the resultant force up there. The resultant force is 0, so the acceleration would be 0. He's still going to carry on moving, he's still going to be moving at maximum speed, but he's just not going to get any faster. Once the drag is equal to the weight, he's not going to move any faster at that point. So the drag is proportional to the speed that he's moving. The more he moves through the fluid, the more he has to push the particles out of the way, the more force the fluid acts on him. And so the drag builds up more and more and more. But he can also increase the drag by increasing the surface area. So if he opens up his parachute, suddenly he ends up with this situation. So he did have his weight acting down and his drag acting up, and the resultant force was 0. So we can say Ft, F total, was 0. But then when he opens his parachute, then he's going to increase the air resistance hugely because of the surface area. So the resultant force will not be 0, and the drag will be much larger than that. And that means, and then again, this is leads to some confusion. Some students might say, "Oh, does that mean he goes up?" No, he doesn't go up, but the acceleration is up. But he is currently moving down quite fast, and so what happens is he slows down, and he then eventually, because he slows down, of course, then the drag reduces, just like it did. So it's the opposite reason for the last time it increased, because the speed increased. Now the speed's reducing, so the drag reduces. And eventually, you're going to have, with this new surface area, a new terminal velocity. He has to slow down to a slower velocity. Remember, the air resistance is a result of the speed that he's moving and the surface area, amongst a couple of other things, but we're focusing on the surface area and the speed. So now the drag is once again cancelling out the weight. So the resultant force is back to 0, but this is at a much lower speed, and so it's safe for him to land. So if we look at the graph, it starts off at the beginning, high acceleration, so very steep velocity. This is a velocity time graph, a speed time graph. So a very steep gradient. And then the gradient gets less and less and less because the acceleration is reducing, so the gradient's reducing. The gradient is basically equal to the acceleration. Eventually, the gradient is 0 because there's no acceleration, and so he's not getting any faster. And then suddenly he opens his parachute. The gradient is now negative because the acceleration is negative. So he decreases in speed very, very rapidly. And then it evens off because, once again, the resultant force is 0, so the acceleration is 0, and he's reached his new terminal speed. But his new terminal speed is much lower than his first terminal speed, because in his new terminal speed he has a higher surface area. Okay, and then this last bit is just when he hits the ground, and that shouldn't be vertical. It should still be very, very steep, because nothing. If it was vertical, that would mean an infinite deceleration. If you have an infinite deceleration, that can only be caused by an infinite force, which can't possibly happen. So there will never be a vertical line on that graph, if it's correct. Okay,